other than ocean components, we're going to look at land and atmosphere and atmospheric composition. And our first speaker today is Ruby Leung. She is a chief scientist for EVSM model at DOE Pacific North National Laboratory, and she's going to talk about uncovering the interannual predictability of 2003 European summer heatwave into the Tibetan Plateau. So please welcome Ruby.
All right. Thank you very much. And I really appreciate the invitation to present and also allowing me to participate virtually. Again, the topic of my presentation is to look at interannual predictability, and particularly related to the 2003 European heat wave. We are all familiar with this diagram over here, kind of showing the sources of predictability at different time scale. And I want to particularly highlight soil moisture that is written over here. So most of us kind of consider soil moisture can provide predictability, perhaps mostly on the time scale of weeks to like a season. But I kind of question whether this might be the case, or whether soil moisture could potentially provide us with a source of predictability at longer time scale. So the reason is that number one, soil moisture itself can probably have a little bit longer memory in certain regions beyond a season. And secondly, soil moisture could also potentially affect the ocean, which has a longer memory, and through the impacts on the ocean, potentially then soil moisture can extend predictability at longer time scale. So this is essentially what I'm going to talk about today. So, but also besides soil moisture, it's also important to consider soil temperature as well. So we are following a decadal prediction experiment protocol, and it was particularly interesting to note that a lot of models participate in the CMIP-6 decadal prediction experiments, and most of them, they try to initialize the ocean, because of course the ocean is definitely very important on decadal time scale. So they use different methods to do that. And some of them also initialize the atmosphere using nudging or other techniques. But interestingly, none of the models that participated in CMIP-6 decadal experiment do anything related to initialization of the land surface. And probably this is reflecting our understanding that perhaps the land doesn't matter that much at the decadal time scale. So again, so this is what we are trying to show, like whether indeed land can provide a longer predictability at a longer time scale. So my colleague Peng Fei already presented a poster yesterday, I think. So he talked about this particular data assimilation system that we have incorporated into two different models. The first one is the EarthGOES model, which is a Earth system model developed in China. And the other one is the ETHRESM model, which is the US Department of Energy's model. So with this data assimilation system called DRP-4D-VAR, we perform a set of experiments. So number one, we just run running fully coupled simulation for like 30 to 40 years. And then we also perform simulation where we continuously assimilate monthly soil temperature as well as soil moisture. One set of experiment, we assimilate soil moisture and temperature globally everywhere over land. And then there is another set of experiment where we assimilate soil moisture and soil temperature only over the Tibetan Plateau, not everywhere else over land. And then we also have a set of hindcast experiments. So these hindcast experiments essentially take the initial condition coming from the data assimilation run, and then we initialize the hindcast experiment with 10 different ensemble members. So the hindcast G take the initial condition from the Assim G, whereas the hindcast take the initial condition from Assim, where only soil moisture and temperature were assimilated over the Tibetan Plateau. So these experiments following the CMIP-6 protocol, they are 5 year long, and we performed 10 ensemble members. And so they were initialized months apart between April to January, and then separated by 5 years. So these are the years that we use to initialize the model and then perform these experiments. So now I'm going to show you some of the results. Particularly want to highlight that because we follow the experimental protocol, so we have a set of hindcasts where everything was initialized in 2001. So we are mostly focusing particularly on this set of hindcasts to look at the 2003 European heat wave. And so here I'm showing you the hindcasts coming from initialization using the atmosphere, the land, and the ocean state coming from the assimilation run where soil moisture and temperature have been assimilated everywhere over land. And so I'm showing you the June, July, August average based on observation data. And so the contours are the 500 hectopascal height anomaly, and then the colors are the surface temperature anomaly. So you can see in 2003, in the summertime, there is very strong anomalies of 500 hectopascal height, and as a result of the high pressure sitting over Europe, there was also the really famous 2003 European heat wave that actually lasts for like a month or two. And so here I'm showing you two set of simulations from two models. One is the FGOES model, and the other one is the E3SM model. On the top are the control simulations. So these are completely free running, fully coupled simulation. So of course, we do not expect these fully coupled free running simulation to be able to produce anything that would look like the observation for 2003 summertime. But interestingly, when we look at the hindcasts where we initialize the atmosphere, the land, and the ocean coming from the data assimilation runs where soil moisture and temperature were assimilated everywhere over land, we see that in the FGOES model, it was able to capture these anomalies of the 500 hectopascal height with high pressure sitting over Europe, and therefore also warm temperature anomaly as well. And this is the same for also the E3SM experiment where we were doing exactly the same thing. And we also see these anomalies of the pressure as well as the anomalies of the surface temperature. So with that, we were really motivated to take a look at why the model is able to predict the 2003 European heat wave when we initialized the hindcast back in 2001, which is like 2 years ahead of time. So now we look at, put our attention into hindcast where the initial conditions were taken from the assimilation runs where everything, soil moisture and soil temperature were only assimilated over the Tibetan Plateau. And so the hindcasts were again initialized in 2001, and we look at the 2003 European heat wave. So interestingly, when we look at the observation, the control simulation, and then the hindcast, again, even when soil moisture and temperature were only assimilated over the Tibetan Plateau, the hindcasts were able to capture these pressure anomalies as well as the temperature anomalies. And as a result, we also can see that there is also soil moisture anomalies as well. So during the summertime of 2003, there is a dry soil moisture anomaly associated with the warmer temperature and the high pressure. And as a result, we also see anomalies of the radiation as well because of the high pressure allowing more sunlight to come through. So then interestingly, the hindcast able to capture all of these anomalies initialized in 2001. So here I'm showing you this vertical profile, and you can see actually associated with these pressure anomaly, we can see something kind of looking like the Rossby wave. In fact, this is showing you the barotropic structure of the anomalies, suggesting that this is indeed related to Rossby wave that is a long-range propagation, probably excited from the Tibetan Plateau, or potentially could also be excited from the ocean. So in order to again understand why our hindcast is able to predict the European heat wave 2 years in advance, so we perform a set of sensitivity experiments to isolate the sources of predictability. So this is the hindcast experiment that I just showed you in the previous slide, where we take the atmosphere, the land, and the ocean initial condition coming from the assimilation run. And when we look at the pattern correlation of the temperature with the observation, it has a very high pattern correlation of 0.82. It was capturing these like warm, cold anomaly that I show you. And now I'm going to show you a few other sensitivity experiments. So the first one is here. So here we keep the initial condition the same as before, except that for initializing the land, we just take the land initial condition coming from the freely running control simulation. So it has no information about whatsoever in 2001. So with this, replacing the land initial condition, now we get a PCC actually of minus. So it shows that when you replace the land initial condition, you really basically have no predictability of the European summer heat wave. And then another experiment where we do the same thing as hindcast. The only difference is that now the land initial condition is also taken from a sim, but we only take the initial condition from a sim for the Tibetan Plateau, and elsewhere we take the initial condition from the control run. And we already recover pretty much the same PCC value, suggesting that the reason why we were able to predict the heat wave is because we have a better initial condition of the soil moisture and the soil temperature over the Tibetan Plateau. And then secondly, I also wanted to look at whether the ocean can play any role. So here we compare two sets of experiments. The main difference between these two is really that in one experiment, we replace the ocean initial condition coming from the control simulation where it has no information whatsoever about the condition in 2001 because it's a free running simulation. And then in this other simulation where we take the initial ocean condition from a sim, where the ocean has been influenced by the soil moisture and the soil temperature because our data simulation is done within a fully coupled framework. So the soil moisture and the soil temperature that we assimilate into the model can influence the atmosphere as well as the ocean. So now I'm going to show you comparing these two simulations to isolate the effects of the land initial condition, and then comparing these two simulations where we can isolate the effects of initializing the ocean. So again, the first one is to isolate the effects of the land. So when we compare these two simulations in spring of 2003 before the European heat wave, we find that there is a big difference between the two, especially over the Tibetan Plateau in terms of the snow cover fraction. So in the simulation where we assimilated soil moisture and soil temperature, there is less snow cover over the Tibetan Plateau, and as a result, there is a warm temperature anomaly which could potentially then excite Rossby wave because of the heating at a very high altitude. So potentially then this is really giving us the predictability, and you can now see these anomalies over here in Europe. And next, we compare the other two sets of simulation. Again, as I mentioned before, the only difference between these two simulations is that one is taking the initial ocean condition from the control, and the other one is taking the initial condition from the ASIM. So we look at January of 2001 as well as January of 2003, shortly before the heat wave. So let's take a look at the SST anomaly. So this is based on observation. So in January of 2001, there is cold temperature anomaly, particularly over the tropical Atlantic as well as the tropical Pacific. In this simulation, where the initial ocean condition was taken from the control free running simulation, it doesn't look anything like the observation at all. But when we take the initial ocean condition from the data assimilation run, which was influenced by the soil moisture and the soil temperature, we see that there is some correspondence between this simulation and the observation in that it also captured a colder tropical Atlantic as well as colder tropical Pacific as well. And then when we look at the January of 2003, again, we see the observation showing some anomalies, particularly cold temperature anomaly over the North Atlantic, which potentially could have an impact on the European heat wave. In this simulation, where the ocean initial condition was taken from the control free running simulation, it doesn't look anything like the observation at all. But in this simulation where we initialize the ocean using the data assimilation run, even 2 years after initializing the model in a free-running hindcast simulation, it has retained some memory and actually produce a negative or cooling over the North Atlantic that looks somewhat like the observation. So in short, we can kind of summarize what is happening. We think that by assimilating soil moisture and soil temperature over the Tibetan Plateau in a continuous data assimilation run, and then taking the initial condition from this, we think that it is affecting the snow cover anomaly over the Tibetan Plateau in spring. And this is causing a warming over the Tibetan Plateau, which can cause a heating, and this can excite Rossby wave and potentially affecting the European heat wave. But this is only one pathway. We think that actually potentially the ocean can also help, because we showed from the sensitivity experiment that by even only just assimilating soil moisture and temperature over Tibetan Plateau, it has an influence through the couple or the weekly couple data assimilation to be affecting the sea surface temperature, so that in spring of 2003, it actually gets a cooler SST anomaly over the North Atlantic, which potentially can excite interdecadal circumpolar teleconnection pattern, and this is also potentially contributing to the predictability of the European heat wave. So I know that these results are actually quite surprising, because we don't think that heat wave could be predicted 2 years in advance. But I want to show you some previous studies that suggest that actually Tibetan Plateau is really important. A previous study, for example, based on observation data, showed that the snow cover over Tibetan Plateau can actually explain about 30% of the heat wave frequency over Europe, suggesting that there is indeed a link, even based on observation. And secondly, there have also been studies that talk about how Tibetan Plateau can have an influence on the upstream climate through excitation of the Rossby wave, as well as by changing the overturning circulation. So these are supporting like our conclusion of why we are seeing this type of predictability. So just very quickly, another set of results where we look at the data assimilation run, where we continuously assimilate soil moisture and soil temperature in a weekly couple data assimilation system. Even in this type of simulation, we find that the simulation, which is a free running, other than just being controlled by the soil moisture and temperature, already get a much better reproduction of the positive and negative phases of the NAO, as well as the PDO and the AMO, suggesting that indeed the land surface, including soil moisture and temperature, can have a very strong influence on the ocean through perhaps by changing the atmospheric condition. So now I'm just very briefly summarizing our results. So soil moisture and temperature has important effects on interannual to decadal predictability. We show that by assimilating soil moisture and temperature over Tibetan Plateau only can improve the hindcast of the 2003 European heat wave, which is actually quite an abnormal heat wave, because this heat wave is not really like an extreme weather event that might last for only a week or two. In fact, this European summer heat wave, the anomalies last for like a month or two, and suggesting that this is actually a climate anomaly that potentially could be predictable. We show that by initializing hindcast using the balanced states from this type of weekly couple data assimilation system with soil moisture and temperature can enhance the skill. And we also show, especially with Pengfei's poster presented yesterday, that this particular data assimilation system, a 4D VAR system that we use, reduces model drift, which potentially also contribute to why our method works quite well in providing the predictability. So with that, I want to thank you very much for your attention, and I'm going to stop sharing to see if there might be a minute or two for questions.
How many ensemble members do you use in your hindcast experiments to see how significant this improvement was?
We use 10 ensemble members. Yeah. But interestingly, previously, we actually only used 3 ensemble members. We get actually results very similar, but we did extend it to 10 ensemble members for the hindcast, for the results that I show.
Thank you. If you have more questions, please submit them through the Slack to Ruby.
All right. Thank you very much.
Thank you very much.
Yep.
Our next presenter is Sanjiv Kumar from Auburn University, and he's going to speak also about land initialization and how it contributes at subseasonal scale. Good name. Oh. Oh, sorry. Sorry, it's Clara Draper. I'm jumping the gun. From NOAA PSL, and she's going to be speaking about initializing land surface states for SFS. Thanks.
Thanks, everybody. Yeah, so I'm going to present our plans for initializing our land states at NOAA in our new SFS system. I should emphasize that this is a very new project. We've only been working in earnest on it for about 2 to 3 weeks. And that's because initially we had thought that we would initialize the SFS system from a reanalysis that we're working on at the moment, but we realised that's not going to be ready in time. So what I'm going to present today is effectively Plan B. Okay, so as Ruby just explained far more eloquently than I can, land initialization can be important at SFS and longer timescales. The particular variables that we've picked out here that we believe are important is both soil moisture, but also snowpack. Soil moisture tends to get most of the attention and probably is the more important of these two, but I think it's important that we don't neglect the snowpack. Vegetation is also really important at these timescales, but I'm not going to talk about that today because I'm mostly talking about the initialization of our prognostic variables, and we don't yet have prognostic vegetation in our model. And I believe Fanglin might touch on that in his presentation tomorrow, or at least our efforts to move towards more temporally varying vegetation. So then the other thing I've just noticed here is that for SFS, we need land initial conditions for 2 different systems, for the real-time forecasts, but also for the reforecasts. And I think it's important that we don't neglect to think carefully about how we do our reforecasts. These are really important because we use those for monitoring and understanding our system, and for things like developing the climatological mean against which future anomalies are going to be measured. Okay, so before I move on, I've just included one slide here that, for want of a better title, I've called land model consistency. What I'm getting at here is that in an Earth system or an atmospheric model, the land is simulated within the model's physics routines. And as with all other physics routines, the land physics tends to be tuned to give you the answer that you are expecting for, let's be honest, atmospheric forecasts, based on the climatology and the other physics that you have in your model. So there tend to be a lot of compensating biases in there that will tune the land model around. This is made more complicated for the land by the fact that for many of the fluxes and states that we're simulating, we don't actually know what the true variables are because they're very difficult to monitor to observe at global scales. And one of the big consequences of this is that if the model's climatology is changed in some way, so for example, if we change the precipitation, this can have unintended negative consequences on the land atmosphere fluxes, even if we improved the precipitation. And yeah, if you take one thing away from this presentation, this is the point that I want everyone to remember. And we've never quite managed to prove this, but we believe that this is what happened with GFSV 16, which is our current global NWP system. So for that, we introduced a system to basically retrospectively correct the soil moisture to account for recent errors in the precipitation. And what that did is it reduced the precipitation over the US, which we think is probably one of the main causes of the increased low bias in Cape over the US. Because we changed the climatology of the model without retuning the land model to compensate for that. Okay, so moving on. So in terms of land initialization for SFS, just to reiterate, we want land initial conditions that are consistent with our model and consistent with our climatology. We want to also want to accurately represent recent anomalies, because of course that's where we're actually going to get that potential predictive skill from. And so this is something like, if we have an unusually dry summer, we want that represented in our initial conditions. And then finally, we also have to have consistent initialization states between our reforecast and our forecast. The general approach that's taken at most centres is to initialize forecasts from an operational analysis, typically an NWP or perhaps a reanalysis if you have one. And then for the reforecasts, these are most often initialized by spinning up an offline version of the land model within the SFS system. And then if there are differences between these two systems, I think Bill touched on this yesterday for the Canadian example, there might be some sort of rescaling or correction to account for that. So what we're planning to do at NOAA is a version of this. So in our current system though, CFS V2, we initialize both the land and the atmosphere in forecasts and reforecasts from CFSR, which is our reanalysis. However, CFSR is quite outdated at this point, and in particular, the land model in CFSR is the NOAA land model. But for CFS V1, which is our next SFS system, we'll be using the NOAA MP land model. So this isn't really an option for us at this point to use CFSR anymore. So what we're planning to do is for the forecasts is to do pretty much the same as what everybody else is doing, or most people are doing. So for the forecast, we'll initialize these from a real-time analysis. And then for the reforecasts, we'll use an offline system that I'll talk a little bit about later. For the real-time system, we're taking the operational analysis from the future GFS V17, which will be our future global NWP system. This will include land data assimilation to help with the representation of those anomalies. So specifically, we have upgraded the snow data assimilation system to a 2D VAR that's implemented in JEDI. And we're also working on ensemble common filters, soil moisture and soil temperature analysis that will be strongly coupled with the atmospheric DA. I've included two slides on this just for if anyone wants to have a look at the DA details, but in the interest of time, I'll just zip straight past them. Moving on to the reforecast, which I think is probably the slightly harder one of these two in terms of just finding a pragmatic solution. So again, we want initial conditions that are consistent with our model and also with our real-time forecasts. And then we also, to the extent possible, want to be able to get an accurate representation of recent anomalies in these initial conditions. So for the SFS project and also for the GFS, we've been doing a lot of development and testing in the models, and the land modelling team here at EMC has developed a system to produce initial conditions for those tests by forcing an offline version of our land model. So it's the exact same land model and same version as is used in the SFS system. And then we're forcing it with Error 5 forcing. And then for the last 2 years of that spin up, they'll activate the snow data assimilation just to improve the anomalies in the snowpack. I've just put a note here to note that we're not doing the soil analysis in this offline system because we don't yet have an offline way of doing that soil analysis. I have some thoughts about how we could develop that in the future, but that's for the SFS V2. So for SFS V1, we are basically going to adapt this system that we already have in use. The reason that we don't want to directly use this is that, of course, the Error 5 forcing is going to be sort of climatologically different from the GFS or SFS forcing. And so if we were to use that, we would wind up with initial conditions that are a little bit different from what we're using in real time. So to get around that problem, the approach that we're investigating at the moment is to rescale some of the Error 5 forcing fields to match the mean calendar monthly values that we would expect from our SFS V1 system. So ultimately, we will tune that rescaling with our parallel runs, which will be a 6-year parallel run. It's not as long as we'd like, but it's what we have. So while we wait for those parallel runs to be ready, at the moment, we're just testing this method just to see if we can actually reproduce land initial conditions that look like they've been forced with our system by rescaling Error 5 forcing. So to test this idea, while we wait for GFS V17, we're using atmospheric forcing from CDAS. CDAS is the data assimilation cycle within our current analysis, CFSR. And we've just started on this fairly recently, and here are some slides that Yulong Xia sent me. So what he's done here is he's done 2 different spin-up runs, both for 11 years. One, he forced our model with Error 5, and the second one, he forced it with CDAS. And then what he's got plotted here are the differences. In layer 1 soil moisture on the left, I don't know if you can see the figures on the colour bar, but it goes from -0.2 to 0.2 metres cubed per metres cubed. That is a huge difference, given that the range of soil moisture is kind of 0.5. Likewise, for snow water equivalent, that goes from -100 to 100 millimetres. So that's like over a meter of snow depth. So these are very large differences. These differences are probably so large because CDAS is so old. And we're not surprised by this result. When you compare the forcing from the two, they're also very different. The interesting result here, though, is, and unfortunately I don't have a plot for this, but when you compare the spatial patterns in the soil moisture differences to the spatial patterns in the precipitation differences, you get the expected strong correlation that you want. And in fact, just earlier this week, Leung finished a run where he did another spin up where he spun up with the Era 5 forcing, but he rescaled the precipitation to have the same monthly calendar mean as the CDAS precipitation. And then when he did that, a lot of this soil moisture differences were greatly reduced. The snow, unfortunately, is going to be a little bit more complicated. So if you notice here, all those blue colours, this is CDAS minus Era 5. That means that we are lower than Era 5 in terms of snow on the ground. But then if you look at that plot on the right, this is the difference in the January monthly mean precipitation. You'll notice that we've got a lot more precipitation. So the differences in our snowpack on the ground is not due to differences in our precipitation. It's actually due to differences, well, it's due to differences in our temperature, which is what's shown on the plot here on the left. So basically our model is much, much warmer than Era 5. And so even though we have too much precipitation, too much of that is probably falling as rain rather than snow. It's possibly also that we're melting off our snow too quickly. So what this tells us is that if we're going to take this approach and we want to get the snowpack right, we're going to have to rescale the temperature in addition to the precipitation. And so we're just starting on this now and starting to look at, because one of the things about that is that we're going to have to address the diurnal cycle, because it's very specifically where we are in relation to those snow processes that matter, not just the net daily bias. Okay, so last slide. So for SFSV1, land initial conditions will be provided by an operational analysis in real time and then by offline spin-ups driven by rescaled Era 5 forecasts for the reforecasts. We're currently testing this rescaling approach using CFSR as a stand-in. And then just as I said, at this point, we know we're going to have to rescale at least the precipitation and the temperature. We'll probably also have to adjust the humidity once we change the temperature to match the relative humidity. So it's sort of gradually becoming more complicated. I also just have noted here that the differences between CDAS and Era 5 are really very large. And in some ways, this is a good test case because it's a much more difficult one. But I'm a little bit wary of the fact that perhaps we're creating work for ourselves by starting with such a complicated case, when in reality, I would expect GFSV 17 to be a bit closer to Era 5. And then separate to this work, Phil Pedgen at PSL will start on some work trying to pin down exactly how sort of consistent the land initial conditions have to be in order to produce consistent SFS forecasts. And then I've included some bit at the bottom here that I don't think I articulated very well, but the point I was trying to make here is that I also think now is a really good time to sort of look forward and to think about this as a long-term solution instead of just sort of coming up with an initialization strategy for now. I would like to also start thinking now about what we're going to do for SFSV2 and to see if there are any decisions that we can make now to try to make this a simpler process in future iterations of our SFS system. Okay, that's it. Thank you.
Questions from Clara?
Okay, the subsurface moisture difference, those that one
Yes, we have looked at them. It looks, as you would expect, very similar differences. But you're right that's what would matter the most.
Another question. Okay.
You're confused about your terminology. So SFS is
Yes,
4 years away. Implementation of SFS is 3-4 years away.
Yes.
It would have its own reanalysis by that time, or at least it's proposed it would have its own reanalysis.
It's not going to be ready in time to do the reforecasts.
Reanalysis.
The reanalysis, the new, I don't know what the new reanalysis is called. I'm looking around the
It
room.
doesn't have a name
It
yet.
doesn't even have a name yet.
It will not have its own reanalysis.
But that was the original plan, was that, so, well,
So you're not saying yes or no?
She's speaking,
well, so.
we need to discuss this more tomorrow, but yes, there is no path forward right now to produce a reanalysis in
Okay.
time.
My understanding was it would have its own reanalysis.
That is the plan. We don't have the resources.
Okay, let's take that conversation.
There is a replay to Era 5, but that's all.
And
Another thing.
maybe one more, come on the left, I'm sorry, I can see your name.
Yeah, question about the version of GDAS-17. Why not use previous version like 16? Like, is there a big jump between the versions? Is that why?
Yeah, it's going to be a very significant update from 16 to 17. 16 has NOAA, 17 has NOAA MP, but even without that, it's a very, very dramatic change. We're also introducing a lot more land data assimilation. So yeah,
Okay.
yeah.
So that trajectory for that
Yeah.
17 is like 2026, 27.
Yeah. Yeah.
Okay, more questions on the coffee break. And in a slide. Now let's have Sanjiv now, sorry for mixing up with them, Kumar from Auburn University to come and give us a presentation about land initialization and its contribution to subseasonal forecast. Is he online?
Can't see him in the room.
Oh, he's
I
not
don't
in the
see
room,
it.
he's online.
Yeah,
Oh, he's online.
Oh, yeah, just share your screen.
yeah, for some reason my screen sharing is not working. Can you, I have uploaded a PDF. Can you please share it there?
But yeah, maybe we could.
Should I just run it or I drive it then or?
I think we're gonna drive it because
Yeah,
it will be faster. So we didn't realize you are not in person. So you're not listed in person.
Yeah, I didn't. I'll present that. I'll present the screen. Just, you can share screen.
Can you share your screen?
I tried it. It is not allowing me to share the screen.
Okay, let's just go with us driving the
Oh, okay, well, we'll drive it
In
then,
it-
that's fine.
interest of time.
Yeah.
Okay, I'll just, we have your slides, if
Mhm.
that's okay, we're gonna go up over here.
Okay.
And, yeah, just basically say next slide when you want to advance.
Okay.
There we go.
Okay.
Oh, gotta go back one. There we go.
Yeah. Thank you, everyone, and I appreciate this opportunity. I think Ruby, she kicked off the session very well, so I'll try to be in her shoes. So we'll go. Moving forward, I will try to emphasize more of the application-related quantity that is important for food and water sector. Go to the next slide, please. I'll emphasize this Earth system predictability framework, where we look into different predictability sources and try to gain predictability from land, ocean, as well as the atmosphere. Importantly, this diagram may look a little bit different to you because on the top I have put the land, but hopefully by the end of the presentation, I'll try to convince you why there are different components in this diagram. Next slide, please. In terms of the land processes, it operates under the various other climate processes, but by itself, it is able to impart a signature to the land-related quantity that is sufficiently different from what you would get from the climate only. So if you take a soil moisture time series and run through its spectral analysis, you will find that it has a much redder spectrum compared to the precipitation, which is much whiter. Next slide, please. I'll argue that soil moisture is more a coupled climate system metric. We are doing some more research that is clearly showing it is not either land or either atmosphere, but it is coupling between these two systems that imparts its signature. And it is related to a range of quantity, like whether it is drought, water resources, agriculture, or even feedback to the precipitation. So by focusing on the soil moisture metric, I'm trying to focus upon the coupled climate system metric. Next slide, please. We'll be using in this presentation the CSM2 sub-X experiment done by Dr. Yaga, Richter, and her group. What I wanted to emphasize here, I'll let her describe the experiment. I wanted to emphasize only one point. In addition to one control experiment that is on the top, there are 7 other experiments. So it is 7 times more expensive than what you would get a standard forecast experiment. But what that 7 additional experiment allows us to disentangle where does the predictability come from. And the diagram that I showed you initially, hopefully you will get convinced where does it come from. Thank you. We'll go to the next slide, please. Okay, so how the land was initialized, it is offline CLM run. It was brought into a quasi-equilibrium by recycling the CFSV2 reanalysis several times, 400 years or so. And then we use all the conditions from the land. So when you run the RAN model, they produce the initial condition. And we use that initial condition to initialize the land component in this sub-X forecast. In this diagram, you are seeing in the left panel where we initialize the land and its skill of the small moisture compared to ERA5. And in the right panel or right column, you see the when we do not initialize the land, and there is clearly differences at the initial lead time. Some of these differences get recovered as we go into the more longer lead forecast. You can see in the bottom plot that blue line is when we initialize the land, and the red line is when we do not initialize the land. I'll come back to these points why some of those at 14 days, 28 days lead, some of those things recovers back. But there is clearly differences between the initialized and non-initialized run. Next slide, please. Okay, I'll quickly go through some of the results now. First important thing is soil moisture forecast skill. There are less of the ground truth observation, so it's very much dependent upon which is the reference data set you are comparing against. We compare using the 4 different reference data set, and we found skill varies from with ERA5 showing the least skill, and then the MIRA2 soil moisture is showing the highest skill. It is all the 4 rows are for season, and all the 4 columns are for different data sets. Since skill was varying across the reference data set, we average all the 4 data set for our analysis. Thank you. Next slide, please. Okay, this is the important slide. In each of these columns, you see the skill derived from the individual component. Atmosphere is the first column, ocean is the second column, and land is the third column. It is week 3 to 4 soil moisture forecast. And what we find, land initialization, when we only initialize the land and we do not initialize atmosphere and ocean, it contributes most to the skill. And then the second is the atmosphere, that skill is almost 50% of the land skill. At this time scale, week 3 to 4, in this United States region, the ocean part was contributing less. I'll come back to the ocean part towards the end of my talk. Can you click on this slide, please? There is and if you focus upon the main agricultural region like Midwest and start of the spring, it's or start of the growing season, it is land is the only source which contributes to the predictable component in that region. So that further emphasizes why land initialization is important for food and water sector. Next slide, please. Okay, so there is another way. Since there are 8 experiments, we can look in various different ways. In this case, in the first column, you see the standard forecast when we initialize all the 3 components. All 3 different rows are a different lead time, first 2 weeks, second 3 to 4, and then 5 to 6 weeks. Now we can start removing one of the component at a time. So in the second column, we just remove the ocean. It still didn't change much. You can read those numbers I have also put. Then in the third column, we remove the ocean initialization. Again, skill slightly decreased. And in the finally, when we remove the land component from the standard forecast, and the skill drops almost 50% when we remove the land component. So that means the land contributes most to the predictable part in the case of soil moisture forecast. Next slide, please. Okay, so I wanted to present one detail. If you focus upon the numbers, atmosphere was contributing almost 50% of the land contribution. So land number is 0.38 and the atmosphere number is 0.20. But if I added those numbers, those were not giving me the total skill what we're finding in the standard forecast. So again, that eight experiment was helpful to understand why this is not adding up. And if in the bottom panel where I saw a skill in various neon ecoregion, I wanted you to pay attention to the atmosphere contribution, that is a red line, and then the land atmosphere coupling component, that is your yellow dashed line. So most of the atmospheric skill is coming through the land atmosphere interaction processes, or the way we calculated it. This is what our calculation is showing. So that's why through our assumption, that part of the skill was already included when we initialized the land, because it was trying to bring at least lower part of the atmosphere to its accurate state by initializing the land. So that's why by adding the atmosphere, we did not improve the skill by 40%. We only improved the skill slightly from 0.38 to 0.41. Next slide, please. I think you can click one more time on this. Oh, no. Go back. Okay, so next slide. Yeah, so when does the ocean initialization becomes important? It becomes important in the DJF, and particularly on the coastal ecodomain. So you see various that map, and if you only go through that coastal region, you will find that ocean component, that is the blue line, that increases its contribution, particularly if you pay attention to neon O3 region. And once again, where does the ocean contribution comes from, or how does it contribute? We also find that land and ocean interaction in the coastal region, that contributes a significant part of the ocean contribution when it comes to soil moisture predictability. Oh, yeah, next slide, please. I think there is a typo in that slide. Finally, we compared our skill set to other other sub-X model. We were able to find only two of the model that saved the soil moisture forecast, but also only for the full depth. FT stands for the full depth here. What we find in the CSM2, the forecast skill is slightly lower compared to ESRL FIM model in this case. And then we looked into what is the soil moisture to precipitation feedback, that is in your bottom panel. I mean, the initial soil moisture anomaly correlated with the week 3 to 4 precipitation forecast. What we find in the CSM2, those soil moisture to precipitation feedback loop is weaker compared to a FIM model. Particularly if you go to the summer season, it is much stronger in the ESRL model. So that is one of the hypotheses why ESRL FIM model is showing the, or can show the higher skill than the CSM2. Next slide, please. Okay, this is my final slide. Hopefully I explained you each of these components, why I put the land up, and then the ocean contribution increases as we go through the time, particularly in the coastal domain. And then there is a atmosphere component too. And these, by harnessing the predictability from these different sources, we can enhance the food and water security. I'll stop it here and take any question if there.
Thank you. Do we have questions? Go ahead, please.
Hi, Sanjiv, Phil Merrifield. So we wrote a paper evaluating soil moisture skill in CANSIPs comparing to on the basis of ERA 5. It looks like from what you're showing that was not the best choice. It might be sort of underestimating the soil moisture ability to predict in the system. So is there a particular verification product you would recommend? And just to add that for snow water equivalent, where there's also differences between products, we found that doing a multi-product average gave the best results, sort of like multi-model ensemble, but for the verification data.
That is a good question, but I do not have a good answer for you. We still do not know why the different product is showing the different result, but your strategy, that is what we also implemented. We did that multi-product average for our analysis in this case, all the four product average. Secondly, we are doing some more analysis, and what we are finding as we move through the time, like more 2000 and more like 2010 period or so, some of these skill set changes, and maybe there is more consistency in the data set when we go more recent period.
Thank you. Perhaps we'll move to the next presentation by Jadwiga Richter, who also going to continue on the theme of subseasonal prediction and role of initialization for wind atmosphere coupling.
There's no, these guys.
Okay, so
Yeah, so I'll continue on the theme of land coupling and other things. So this is work based on CSM2 with several people at NCAR and also Sanjiv and beyond. And at NCAR, really what we're interested in is understanding the sources of predictability. And particularly in this talk, we're going to talk about the role of atmospheric, land, and ocean initial conditions. And some experiments we've done with land atmosphere coupling, also a little bit about role of data assimilation. So our CSM2-based system, we initialize without data assimilation. It's partly why we're examining the role. So for the atmosphere, we use NCEP CFSV2, so we just interpolate it to our grid. For the land, we run a standalone land simulation forced by CFSV2, and the ocean, we initialize the same way as for the Cato prediction, so it's a standalone ocean force run by JRA 55. And you've all seen this version, this diagram, or this is our redrawing of Paul Diermeier's diagram of where the predictability is supposed to come from. So on these timescales of subseasonal timescales, a large portion is supposed to come from land, and a small portion is supposed to come from the ocean. And of course, there's the atmosphere. So we designed these experiments to really quantify this diagram. And these are the same experiments that Sanjiv described, but I'll just tell them about you a little bit in more detail. So our basic reforecast set follows the SubX protocol. So weekly starts the same day of the week, and we do this from 1999 to 2020 with an 11-member ensemble. And then we ran this same protocol 7 times over. And each one is just slightly different with initial conditions. So CLIMO ATM means that we change just the atmospheric initial condition with climatological atmosphere. CLIMO land means we replace the land that was realistic with climatology and so on. So in these experiments, we take out one realistic component and we change it for climatology, but then you still have 2 other ones that are realistic. So after we saw the results of the experiments on the left, we realized we really needed to do all of the experiments on the right, where only one field is initialized realistically. So that's why CLIMA ocean, CLIMA land, only the atmosphere would be initialized realistically. And in order to complete the set, we ran the CLIMA all to demonstrate So actually the scale is not quite zero. So then we would only be able to take out how much do you gain by initializing the atmosphere, how much do you gain by initializing the ocean, etc. So we're mainly looking at ACC for 2-meter temperature and precipitation. We're comparing to ERA 5 just so we can look at the oceans, but it's the same results if you compare for CPC, overland, etc. Nothing really changes in the conclusions. Okay, so we start with the experiments in the atmosphere. So all these plots are going to be the same way. The top panels are weeks 1, 2, middle 3, 4, and then 5, 6. And the standard reforecasts are just everything is initialized. And the scale of our system is comparable to NOAA CFSV2 and all the other sub-X models. So most of the time we're on par or better than those models. So when you take out the atmospheric initialization, of course, this makes a huge difference. So you see this in the middle column there, that overland, you lose majority of the scale. And this is expected, right? But we just wanted to do the experiment. But if you look at weeks 3, 4, if you just initialize with the atmosphere, if you compare the right column to the left column, you actually see that you gained the majority of the scale back just by initializing atmosphere. So we didn't really expect that, but it is consistent with the rest of the findings. So the most surprising findings are here with the role of the land. So in the middle column, when you change to climatology, you already see that in the weeks 1, 2, when you initialize with climatological land, you get skill that is as good or better when we initialize otherwise. And this continues for weeks 3, 4, and weeks 5, 6. So this is something that we did not expect at all. We expected to pose diagram that this should be really different. And on the right-hand side of the very column is the skill that you gain just by initializing the land. So not a whole lot. You just initialize the land at any time scale. That doesn't get you a whole lot in our model. So we started digging into the land atmosphere coupling. Since the result is not what we expected, we've had calls with Paul. We asked him for what would you be looking at, etc. We also looked into the models. And part of Paul's prior work to show the land was done with CSM1, so an older version of the model. And the colors here look a little odd, but anyway, the main message here is that the coupling between the land atmosphere is not the same in the two versions of the model. So in CSM2, we have strong and negative coupling in the summer hemisphere. Southern hemispheres may be similar to CSM1, but in the northern hemisphere, we have weaker coupling than in CSM1, meaning there is a weaker impact of the soil moisture on the surface fluxes than what are these weak. So it could be that our model is not capturing the land atmosphere interactions correctly. Although these fluxes, if you look, they verify against observations, and the model in general is one of the top CMIP models. So there's some reason to believe that it's doing something right, but it's clearly not getting the interaction. So a lot more work we need to do on this. And we're starting with some land sensitivity experiments, and we are tweaking this parameter, which is the mean coupling parameter, which is right now, this parameter is this coupling strength. It really means that the wet soil fraction necessary to form the dry surface layer. So in our default model, there is 0.8. So we're trying some case studies when we changed it to 0.5, which is what our land people believe is you shouldn't go any lower than that. So now with the coefficient set to 0.5, the soil needs to be 50% dry instead of just 20% in order to form a dry surface layer. So basically, we're just trying to increase the stronger land atmosphere coupling. So we ran a May 6, 2019 initialization, and you can see that it is making results. This is just temperature perturbations over the United States, that it definitely changes what are the temperatures that you're going to get. But the problem is that we cannot figure out what the climatology of the model is, because the only climatology we can take out is from the regular forecast. But we're trying to see the sensitivity of this parameter, but really in reality, we're going to need to once again rerun the entire reforecast suite for 10 years, because the climatology of the model with this parameter is going to change. I'll be curious from the other people in the room who may be working on similar things, how do we avoid running the entire reforecast set or a portion of it to get these sensitivity experiments? So that is one outcome that we didn't quite expect, and it's definitely something we're going to work on in this coming year. So now the role of the ocean. So similarly, we did the same thing with the ocean. And the results here are a little bit more what we expected, but also not quite. So if you look at the middle column with climatological ocean, we also do not lose any skill in weeks 1, 2 over the majority of the land areas, except in the tropics. So the northern part of South America, central part of Africa are the places where we are getting a little bit of signal from the ocean. And especially you see that at the bottom right. So by the time you get to weeks 5, 6, that is really starting to come in and is something that is giving you skill. And particularly this is true in ENSO years. So we looked at the active minus neutral ENSO years and where the benefits of ocean initialization are coming in. And similarly in the bottom panel, you see that it is in the tropical oceans and the continents that are matching tropical oceans. And mostly in weeks 5, 6. So weeks 3, 4 is still borderline, but this is a little bit more what expected. And it's possible that our teleconnections in CFM2 are still weaker than they need to be, but at least if it's a little bit more consistent with what we believe should be happening. So if we were going to draw our diagram based on CSM, and again, this is just one model and it may not be correct, but this is what it looks like on the right, that pretty much the atmosphere is providing most of the skill in weeks 3, 4 and beyond, and we're not getting any benefit from the land. And the ocean is coming along, it's beginning, but it's definitely not like in the diagram. So yeah, the caveats are that this model may not be the ultimate thing. So I would love for other groups to repeat it, but the fact is that the skill of this model is comparable to all the other sub-X models, and some of the time it exceeds the other models. So it has no fundamental flaw. It has just is skillful, sometimes more than others, sometimes less than others, but really fundamentally, there's nothing wrong with it. Okay, so the last thing I'm going to talk about is data assimilation, because we often get criticized that we don't use data assimilation. And I wish we had a couple of data assimilation framework for CSM, but right now we don't. But the only thing we've done is we replaced the CFSV2 initial condition for the atmosphere with that generated by DART, so our data assimilation system. And we've done this 2 ways, and I'm going to show you the initializations with the DART atmosphere and also the land spun up with consistent with that, because we don't have yet data assimilation for land with DART, or at least we don't have the reanalysis going back 10 years. But the short message here is that we gain a little bit of skill by initializing the atmosphere with data assimilation, that you see that all the way in the middle panel on the right-hand side. So that's for weeks 3, 4, a little bit in the northern hemisphere. And weeks 5, 6, we get a little benefit. But data assimilation in the atmosphere, at least this doesn't seem to be the limiting factor here. So I think the results might be different if we were assimilating soil moisture into the land, etc. And that is some of the work we're going to do in the future. But we're just going one step at a time, just taking one variable at a time to do this in the most systematic way that we can. So yeah, again, on the role of the data assimilation, the biggest differences we see are in week 1, of course, and those are only in particular season. So this is just over North America, 2-meter temperature. By the time you're looking at week 2 and weeks 3, 4, you really have a hard time figuring out which one is the line with the data assimilation and which one without. So that's really all I have. And in summary, we're just basically trying to track down where the predictably comes from and which parts of the model configuration matter the most. And it's really nice to see the work on the land coupling, because we're going to put in some resources into that this year to work on that further, including with the NOAA MP model and MPAS. So I think there may be some opportunities to collaborate with some of the people who talked earlier.
Maybe introduce yourself.
Okay, I want to work with CPC. One, your map just show the climate since you use climatology since no damage we are without.
Climatology for what?
Right.
For
land. So, my question is that, because we know the CFS land surface is not good. So,
So our land is initialized with CFS V2 atmosphere driving the land model standalone. So we run it for 500 years old. So we spin up the land model using CFS V2.
yeah, but you use climatology.
The climatology,
Surface,
Yeah.
it looks no damage, right?
yeah,
So that means land surface right now is not important.
yes.
My argument is, since we know the CFS. land surface is not good. So you remove the land surface.
But it's their land.
It's our
not
land,
CFS
so
land.
our climatological land is from our land, so it's still the CLM, but just climatology over the last 30 years.
Okay. So this is climatology.
Can we take it offline?
Yes.
Okay, good. But it's their land, not NOAA.
Yeah.
Okay, next introduce
Yeah,
the
other
companies.
than the wishful thinking, why should we believe that figure drawn by Paul?
Why did I believe this?
Why should we believe? Because
Hypothesis.
Why does everybody in this room put it as their first slide? Right?
It's a hypothesis.
That's a highly conflicted figure coming from Paul.
But it's used in every presentation that somebody gives on S2S, right? So if it's not realistic,
But it's a hypothesis,
it's a
right?
hypothesis, and that is exactly why we set up the study to show whether it's true or
So
false.
we should believe your one, but.
No, you shouldn't believe me. You should rerun the experiments with other models to
Right.
come to a consensus what it is.
And I can almost guarantee if you run by 10 models, your figure will come out right.
That's really interesting.
We'll see.
We'll see.
Yeah, we'll see.
That's a new hypothesis.
That's the new hypothesis we can put for a coordinated experiment.
One more question.
Might it be the case that you should be thinking about land surface in the way that you think about stratosphere? Just shut off the stratosphere most of the time, doesn't really matter. But it's a forecast of opportunity thing where you have to have a large perturbation and then you have something that's important. Might that be a better paradigm? Than
Yes, yeah.
Yeah, so that is on the list. We're now picking out specific case studies and then also trying to look at those main atmosphere coupling parameters in those. Yes.
That's a paradigm. Land doesn't matter, but it breaks everything. I think
Blame it.
I work at UTR. I have just one question. So you mentioned about fixing the wet soil fraction as a mechanism to strengthen land atmosphere interactions. I just wonder, do you have a empirical basis for doing that?
So Meg Fowler, this is her figure. She believes that the number of 0.8 is the best match to the observations. But you can see the dots on this diagram represent where we have observations. So the observations are not super comprehensive. So those are based on FluxNet towers, and those are their best estimates. So they think this is the most realistic, but this is where we're going to start looking at more process diagnostics, see if there's anything else we can diagnose, whether to tell us where that parameter is really realistic.
Thank you.
Okay, thank you very much. A new hypothesis. Yes. So, our next presenter brings us back to the ocean initialization, and Samir Pokhrel from Indian Institute of Tropical Meteorology will present his presentation on improving Indian summer monsoon with ocean initialization.
First of all, I am not Samir Pokhrel. I am Hasibur Rahman, one of the co-author of this paper. I am glad that I am on behalf of him, I am presenting here, and I am visiting here as a visiting scientist for 3 months for ocean reanalysis project. And I got this opportunity, and I thank the organizers for giving me the opportunity to present this physically. Well, so this is a kind of case study we did with the new ocean reanalysis things which I did. We did for the GDAS, upgrading this. So before going to present what just little bit about the background of monsoon, Indian monsoon, how it's affected and what is for the understanding for the audience. See, Indian summer monsoon is the backbone of entire Indian region. So it's basically it's a huge system, land ocean system, which moisture transport from the Indian Ocean, and it's being rained during monsoon, June to September, 4 months. And every year, 30 to 40 million people are affected by floods during this season. And not only that, during drought time, if it is droughts, it's more than 330 million people affected by these droughts. So very tragic event happened in last month itself in one part of southern part of one state, Kerala. So 30th July to 2024 in Wayanad, there was a landslide. Two entire village was washed out. And then there were more than 400 people died, and many bodies were found after 3 to 4 kilometer downstream in that sense. So this is the things happening in every year, and one part of this is like, so other than this, economical things is also is huge for this Indian monsoon. You can see the GDP in the good monsoon can enhance 3% in Indian GDP. And in every year is 700 billion USD cost damaged by these floods every year. And very recent study shows just the change of this climate change, how it is affecting the entire Indian monsoon states. Some of the states like Gujarat, Rajasthan, and Maharashtra are the arid, so-called, these are the arid kind of zones, where now last decade or so, 10 to 30% more southwest monsoon rainfall is getting in these districts, these states. And other than that, those are Gangetic plain where you need to be very active and getting rain. They are reducing this 10%. And these are some of the things which is this in study, some old studies. It shows that how much it is every year is affected by life lost and then economic loss, as well as people affected in millions. So what we study is here is for this study, Indian monsoon prediction is very challenging, and mostly because of this intra-seasonal variability, intra-seasonal oscillations called MISO, monsoon intra-seasonal oscillations, which from equatorial Indian Ocean and is propagate all the way to the northern Bay of Bengal, and it brings a lot of rain to the Indian. So these are most of the models are unable to propagate this northern propagation MISO. And after evaluating many models during 2014, it seems it's come out to be CFS V2 was the best among all the dynamical models, couple model. And then Indian government started a project, the monsoon mission, and we identified the CFS V2 for our workout for the monsoon predictions. And right now, the seasonal predictions is happening using the CFS V2 every year. And what we did is, after getting this model from here, we try to upgrade this model, changing some of the aspect, like we changed this, when we got this initially, it was only single layer snow scheme, and we made it as a 6 layer. And after doing when we got the initial, the scale was 0.56, and by changing this snow, we got this 0.61. And after was another one very, promising things we did is changing this cloud microphysics modification in that. So after that, it is enhancing 0.71 also. So one of the things is like the changes in this cloud microphysics, this accretion of rain and snow, which was absent in the original physics. So we use this in this new experiment. What we do is we use this initialization with MOM4 P1 GDAS, which was we did. It's a kind of case study, 8 years simulations we did from 2011 to 2018. So we did 2 experiments. One is control experiment where this NCEP CFS-V2, the original one we used. And then we use the new initializations with this new reanalysis things which we made using this MOM4 P1. The other thing is this one is a huge improvement we found in Indian Ocean particularly, and global ocean as well, which is documented in these 2 papers. And we did 5-day interval this ensemble 5, 10, 15, 20, and 25th February. And 4 times we use for this every this ensemble member. And we did 20 ensemble for generating this thing, and then for 9 months from this 11 to 2018. And this why we use the February initial condition, because there are studies shows that February initial conditions has a high skill in Indian monsoon seasonal predictions. So these are some of the improvement what we got is this one. What he sees is the ocean, how it's improved in the ocean. This is the heat content up to indicated 700 meter. This is the correlation for with respect to EM4, and you can see the new initial condition initializations, how it is improved entire Pacific and Indian Ocean also it has enhanced. And this is a transition in the Pacific and how this heat content bias is reduced in this new NIC bias compared to the control. And this is the interannual in NINO3 region average. You can see with the new IC, it's going back to back with this EN4 analysis compared to the new initial, the controlled one. And this is another one, temperature, how it is improved in temperature correlation in depth along the transect of entire equatorial zone. And this is enhanced in entire Pacific as well as Indian Ocean, also this Atlantic. And this most important is NINO3 region, which is kind of 40% interannual variability of the Indian monsoon comes from this El Nino. So this NINO3 is very important region for that, and it has enhanced, this bias has been reduced drastically, and as well as the Southern Indian Ocean. So these are the skill improvement in, we see how this individual, this ensemble member also performed on different regions, different this SST. And you can see each and every region, this is being enhanced and improve the skills. And this is if you average all this ensemble, and this is control, and this is new AIC, and this skill has improved drastically. And this one is this is the Taylor diagram of all these individual ensemble members. And this one is all India and Central India. Central India, one of the biggest challenge of all these dynamical models is Central India is dry bias we get every models. So this with this new initializations, we could able to get this Central India lane quite improved. And these are you can see this all this 99% confidence level. This is the control one. This is with new IC, and all these most of these ensemble members fall in this quarter only. And this block, this circle, this squares shows this control and ensemble. You can see even the Central India, it is the negative skill almost 0.1 minus, and where is going 0.6 near about in this. And also we found this what is the cause for this improvement finally. Some of the things like we see the assisted drift, which is there in the control, which is much reduced in this new years I see in the 1 month lead and also the 4 month lead. And not only that, this assisted drift in the NINO3 region also much improved in this new IC. And along with that, the atmospheric circulations also improved. What is the monsoon jets and monsoon indices, which are the most widely used indices to see the monsoon strength. Monsoon index as well as Webster index also enhanced in this new IC experiment compared to the control one. It's a huge improvement, and also this integrated moisture flux skill also improved in this new IC. These are some of the things why this skills has improved in this new IC for the Indian monsoon, Central India as well. So this is as a nutshell what it shows is if you see this is the ocean heat content improved, and then with that atmospheric circulation pattern also Hadley cell and Walker cell also enhanced, and that's leading to the enhanced skill in the summer monsoon, particularly the Central Indian region. And these are some of the summary of this accurate initial conditions is very important. What we found is ocean initializations. And then models with better mean also is required, and this model shows a better mean and which leads to the better interannual availability. And these skills improve from 0.14 to 0.51 in this new experiment. And it's needed to be what we found is the couple data simulations is required for this improvement further, which we found. And this is kind of my role was mostly the ocean part, and these people, my collaborator, they use the CFSV2 mostly. So if I'd be glad if any questions are there.
Questions? Everybody's excited about coffee.
Yeah.
Okay. If you have more questions out of energy, please feel free to speak during the break.
Yeah.
Okay, now we're going to our last talk, and hopefully it's the right speaker. It's Cory Martin from NOAA and NCEP and EMC, who's going to speak about global data assimilation for aerosols.
Thank you so much. Yes, we will make sure we get into the coffee break on time. So before I get started, I just want to make sure to acknowledge all the co-authors, and particularly Andy Pangborn and Yaping Wang, who did most of the work that I'm presenting here. So we're going to talk about the plans for aerosol data assimilation for the next version of the GFS. Currently, EMC or NCEP, you're one of the few of maybe only operational centers that has an aerosol prediction system but do not use data assimilation to initialize it. So our plan is to mimic the atmosphere, just like was talked about this morning, or the ocean, where you have 6 hourly cycles 4 times a day with both an early and a late cycle. The early cycle is so we can initialize the GES aerosol prediction system for the long forecast. And the late cycle is to run the cycle DA to initialize the high resolution GDAS forecast without radiative feedback to not impact the atmosphere or the global atmospheric forecast. Our target right now is an analysis resolution of about 0.5 degree, with the background being 9 kilometer as of now that are the targets. We plan to do a 3D VAR FGAT, first guess at appropriate time, with 3 hourly backgrounds and using observations from VIIR's polar orbiting satellites, SNVP as it's still available, N20 and N21 at 550 nanometers. So why are we doing a simulation of AOD for subseasonal prediction? So Yaping Wang did some work a few months ago with a student t-test and suggesting that with albeit a limited sample size, that the VIIR's AOD assimilation can have a significant impact on the model's forecast of aerosol optical depth. So in this plot, we can see a significant reduction of the RMSE out to about 5 days. And they only ran out 10-day forecast for this work and was seeing mean bias reduction that was considered significant by the student t-test out to 10+ days. So that shows that we do see an impact long into the medium range from the aerosol simulation and potentially even into the subseasonal to seasonal range. So thinning versus superopping, for those of you who know DA, you know all about this, but I'll still cover it. The observations of the VIIR's AOD product are about 750 meters, which are far too dense to assimilate all the observations. In data assimilation, we tend to assume that observations are independent and not correlated, which at 750 meters is very much not the case. There's 2 main ways we handle this. We can either do thinning, where we select randomly every observation, or with some sort of space and time structure, or we can do superopping, where we can average and bin observations together into one new observation. We're aiming to have approximately 1 observation per model grid point. So here's some results from Yaping's work, where she showed the comparison of comparing the new observations from VIIR's to the AeroNet ground truth, an independent observation data set. And on the left, we have when thinned, and on the right, when superobbed. And we can see that the bias is reduced, and the RMSE, and the standard deviation, all 3 are improved when doing superobbing versus thinning. So superobbing is the approach we're most likely going to take when we implement this in operations. Here's another comparison of thinning and superobbing, but this time actually running an experiment for a 2-week period. And while the results are a little bit mixed whenever you compare different parts of the globe, in general and over the global average, superobbing reduces the mean bias, the RMSE, and the standard deviation compared to thinning. So just to reiterate, we're going to go with a superobbing approach rather than a random thinning when we implement this. So Travis Jadwiga this morning talked about how one of the great things about JEDI, and I didn't mention this is all through JEDI, is that we can leverage things that have been put in for the atmosphere or for other components and use them for different components. So I'm going to talk a little bit about some of the quality control procedures we were able to use pretty easily because they've been developed largely with the atmospheric DA as the initial focus. So some basic quality control we've added in for the year's AOD include just a simple check on the retrieval quality flag defined by NESDIS. We're inflating the errors whenever the background check that fails, or meaning when the obs differ significantly from the forecast. We're going to make sure that the valid range of AOD is between 0 and 4.9 because you can have a negative AOD in the retrieval, or we have a very large value of 5, so we're making sure we keep it in a more realistic range. And because of the density of observations combined with the fact that polar, when at nighttime you don't have any optical depth, we're making sure we limit the observations between 60 north and 60 south. The next few slides, we're going to talk more about the QC, but also variational bias correction. So we can do this because we have to do, sorry, let me take this back. You do variable bias correction where you correct the bias every cycle based off of coefficients found in the minimization. And normally we'd use an independent anchor like AeroNet, but we can't because of latency issues. And Easton WF has shown that they can use NOAA 20 to anchor other year's observations with variational bias correction. So here's some results again from Yaping Wang of using variational bias correction. On the left is using sulfate, one of the aerosol species, as a predictor, and on the right is using just a constant predictor in the variational bias correction. On the plots, red means that VAR-BC is considered better compared to CAMS, and blue means worse. So when you use a constant bias predictor on the right, you can see there's not a whole lot of impacts, but on the left, we can see that the reduction in error is non-trivial over places like East Asia, India, and Central Africa, and the east coast of the US into the Atlantic Ocean. And there are a few places where it's worse, but overall, using a bias predictor of sulfate does improve the forecast. So because we're running a 3D VAR analysis, the background error covariance is very essential to the performance of the system. So there's been multiple methods we've explored to compute the background error covariance. One is the traditional NMC method, meaning if you lag a forecast from 48 to 24 hours, subtract the difference and use that for proxy for error growth. We have used bump estimates for an offline ensemble. I think a few people this week have talked about bump being a component of GDAS for error estimation. One thing that we tried out recently, again, going back to the beauty of GDAS and being able to use things that were developed from the SOCA application, is we can use a time varying covariance where we use the background from each cycle and compute the variance from neighboring grid points. So this was a quick thing to use because it had already been developed for SOCA, and we can get it basically the flow in the information based off the background without having to be able to run an ensemble. And as of now, our plan for the aerosol data summation system is to run a hybrid of the second and third approaches, blending together a bump estimate from an offline ensemble and the time varying covariance using the neighboring grid points. So here's just some examples of the local variance estimation. So on the left, we have the near surface forecast fields dust in the smallest size bin, dust 1. And on the right is the variance computed from that. And you can see it's largely following the forecast, but with a lower magnitude because it's not the complete value. It's just how within an n number of grid points, how much is it varying. So here's an example of some analysis increments we're getting from the system. On the left, we have the dust near the surface, and on the right is sea salt near the surface. And then I'll show here again the vertical slice of sea salt on the left, and well, I guess both are sea salt. One is a longitudinal slice and one is a latitudinal slice. And the one thing I want to point out here is that all this work is really important because it's very tricky, and our problem is very ill posed because we have about 15 three-dimensional tracers for one two-dimensional observation of aerosol optical depth. So the only way we really can get information on how to distribute the species out from the innovation statistics is based off of the background error covariance matrix. And this all work is done by Andy Tangborn. So here's some comparisons between our system, our prototype system, and MERA-2 and CAMS. So the important thing to note here is that on these plots, the solid lines are compared to MERA-2 and the dashed are compared to CAMS. The left is a bias plot and the right is an RMSE plot. And depending on which So this, I guess, is in the blue is without data simulation and the red is with data simulation. And the important thing here is that the data simulation is improving the forecast overall this time period with these globally average values, but we still need to do more tuning to make sure that we can get the best performance possible through the system. So in summary, work is progressing on our first operational global aerosol analysis capability. This is a JEDI-based system, hoping to leverage a lot of the work that is going into the atmospheric DA, but also the ocean and land surface DA all together through JEDI. It's great in particular with the atmosphere and land because it's all FE3 JEDI, so we really can leverage most of the elements together. Right now, as we speak, even this afternoon, I was just talking to Andy on some of the stuff he was working on. We're tuning the background error covariance and testing out more quality control and advanced observation usage. And the target is to implement this as part of GFS V17, GES V13, which was mentioned before, will be JEDI based for all the components except for the atmosphere. I didn't mention it here, but we also are working on regional air quality EA efforts, meaning trace gases, particulate matter, and also aerosol optical depth at the regional scale and higher resolution. And our longer term plans include ensemble methods and doing a very important thing for this problem in particular, simultaneous state and emissions estimation, because for air quality and atmospheric composition, the surface boundary conditions are just as important, if not more so, than the initial conditions. And then also doing things like strongly coupled assimilation, like the aerosols impacting the radiances to improve the atmospheric DA. And so hopefully I got us through pretty quick, so we can end right on time for the coffee break, and I'll take any questions again.
Before questions. Okay, maybe we start from Madeleine.
Have a comment. It's impressive to see how you are starting collecting the fruits of the investment on JEDI. So it's very good use from not having data simulation to doing advanced data simulation that allows you initial estimation. It's quite impressive.
Next question.
Go back to your earlier stuff when you were comparing the super obbing to the thinning. Are you changing the observation errors in that? Because when you start averaging observations, your random errors should go down.
Yes, and that is part of the equation. So when we're thinning, we're not changing the errors because we're using the error from whatever was the ob that you're selecting. And when the super obbing is using the average of the observations that are included in that.
Oh, okay.
And the super obbing is a little bit more advanced where it's only taking obs that are sufficiently high quality and free from clouds. And so it is going to be a better product just because of that.
Thank you. Next.
Yeah, is the primary motivation predicting aerosols and air quality or improving surface forecasts through influences on temperature, et cetera, or both?
So both is the short answer. I think the jury's still out on how much the radiative feedbacks are going to be included in the short term in the GFS and the GEFs. But in the immediate term, we're definitely mainly focused on improving the aerosol forecast itself and hoping that that improves then the radiative feedback and we include that in the forecast.
We have two more questions. One will start with Stan and then we'll go to the back. Stan.
Great, thanks. So the aerosol has smoke in it, correct? And so we've been, enduring also the price of not having data simulation during the wrap cycling because of that. So do you think that all this will work out well also for modifying smoke and aerosols and with the other aerosol representations for data?
Yeah, so it's a little bit different because we don't necessarily have smoke in the GEFs. We have things like carbon. It's in the HER, it's like one tracer, right? But like I mentioned, we have parallel efforts working with GSL and the DMC on the regional air quality work. So I'm hoping that while we're pioneering it mostly for the global, I think a lot of the lessons learned are going to be applicable to the regional application as well. And it's mainly one of the main applications for this really is the wildfire prediction, including the smoke, the downstream plumes from the wildfires.
Thank you. One more question.
Yeah, thank you for progress. I have a question. Because the observation is mainly either coming from satellite observation or years or aeroplane, they are also followed back. And when you do this observation, it looks to me that it might not, correct the bias in the profile. However, for instance, by GES 13, there's no proof price the aerosol model. So it's made as issue that the injection height of the fire is correct. So how to improve this from this in the future? Do you have any idea about?
And yeah, in the short term, it's not going to be easy because like I said, the problem is very ill posed because we have 15 3D tracers and 1 2D variable that we're assimilating. One thing we can look to in the future is using multiple wavelengths instead of just 550 nanometers and seeing that can help with speciation. I don't really know how to solve the height problem without having like parallax of observations, and it's not an easy thing to do in real time prediction.
Thank you. Let's thank Marty and everybody else. I will finish on that by the technical question. And now we're going to go to the next.